diagonalize the matrix if possible. So we are given this matrix. Diagonalize means if this is eligible to diagonalize, we then find diagonal matrix similar to A and a matrix P of eigenvectors such that, so basically diagonalizing means finding D and P such that this A matrix has the following factorization: P, D, P inverse. If we multiply these three matrices, then we get A. Okay, and now first we need to, we know that D is matrix of, just the diagonal matrix of eigenvalues, and P is the matrix of corresponding eigenvectors. So we need to find the eigenvalues, and to find the eigenvalues we just solve this characteristic equation, lambda I minus A equals 0, or determinant of A minus lambda I equals 0. Okay, these are equivalent. So, and we solve for lambda. So these are eigenvalues. Then to find the corresponding eigenvector, we solve this, we find the null space of A minus lambda I matrix, or lambda I minus A, same thing. Some vector, eigenvector equals 0. So it's pretty much like AX equals 0. So we find the null space of this matrix. Okay, but we are lucky in this question because this is lower triangular matrix. So lower triangular means we can easily find the eigenvalues. Okay, so since A is lower triangular, eigenvalues are, let me write down lambda, 5, 5 and negative 3. So we can just say 5 and negative 3. So 5 with multiplicity of 2 and negative 3. So we got only two eigenvalues. For this matrix to be diagonalizable, from these two eigenvalues, we should be able to get, we need to get 3 linearly independent eigenvectors. So we have to have 3 eigenvectors. If we find just one eigenvector from each of these two eigenvalues, then this matrix is not diagonalizable. So we must find 3 linearly independent eigenvectors. Okay, so to find the eigenvectors, what we do is we just solve A minus lambda I x equals 0 for lambda equals 5 and lambda equals negative 3. So let me find this matrix. What is A minus lambda I? So A is the given matrix, I is the identity matrix, in this case 3 by 3. So 1 0 0 0 1 0. So this is I, and we multiply by lambda. So multiply each component, each element by lambda. So these 3 become just lambda, lambda, lambda. And we subtract this from A. So A is 5 0 0 0 5 0 1 4 negative 3. So A minus lambda I, which is, I'm going to write over here, we just subtract the corresponding components. 5 minus lambda, 0 minus 0, just 0, 0, 5 minus lambda, 0, 1 minus 0, 1, 4 minus 0, 4, negative 3 minus lambda. Okay, so we have this A minus lambda I. Now we take lambda equals 5 and lambda equals 3. So first, for lambda equals 5, so A minus lambda I, so we are trying to find the corresponding eigenvector. V or X doesn't matter, equals 0. This implies Okay, I'm going to write just the augmented matrix. So augmented matrix. So A minus lambda I is here. So we just replace lambda by 5. Okay, and that gives 5 minus 5 0, 0, 5 minus 5 0, 1 4, negative 3 minus 5 negative 8, and that augmented means we don't need to write x, so 0 0 0. Now we do the row reduction and solve. Okay, this x got 3 components, x1, x2, x3. Okay, so this one 0 0 0 always on the bottom, so this one is same as, let me put this r3 in r1, so 1 4 negative 8 0, and doesn't matter, all zeros. Now we got pivot here. This 1 is the pivot. There is no pivot here, no pivot. So this is x1, x2, x3. So no pivot here means x2 is a free variable. So is x3. Now solving this, we get x2 is just x2, x3 is just x3. From the first row we get 1x1 plus 4x2 minus 8x3 equals 0. Let's move this over, means subtract and add. So our x1 is negative 4x2 plus 8x3, and x2 and x3 are free, so this is it. So from this, thus the corresponding eigenvector is just x1, x2, x3, which is x1 is found here, negative 4x2 plus 8x3. x2 is just x2 because it's a free variable, and x3. If we look at closely here, we got 2 types of arbitrary real numbers, because arbitrary real numbers x2 and x3. So I can factor x2 out and a vector, plus x3 out and a vector. So x2 means here negative 4x2, so negative 4 in the first component. x2 means 1, there is no x2, so just 0. x3, 8x3, so 8 in the second component, none, 0, here is 1. So the basis for the eigenspace, we got 2 of them here, negative 4 1 0, 8 0 1, or these are the corresponding eigenvectors. So for lambda equals 5, we got 2 eigenvectors, and next we will find the eigenvector corresponding to negative 3, and we are sure we get at least 1. We always get at least 1. Here we got 2, and we will get 1 more. That means we will have 3 linearly independent eigenvectors. That means A is diagonalizable, and we'll find P and D and B. Okay, so thus so these are the eigenvalues. So let me write in this way, so we can just say that's this one. So for lambda equals 5, the eigenvectors are this one, negative 4 1 0, 8 0 1. Okay, so I'm gonna write over here 5. For 5 I got 2 of them, negative 4 1 0 and 8 0 1. Okay, and now I'm gonna do the same work for 5. I got 2. Now I'm gonna go over and just do the same work for lambda equals negative 3. Okay, So for lambda equals -3, we just plug in -3 for lambda here. So 5 minus -3 would be 800,080,140. So we are here. So on the first row, I can multiply by 1/8. I get this. Second row, do the same thing, multiply by 1/8. I get this. And third row. Now to change this into echelon form, so 1 1, so I'm gonna work on R3 such that R3 plus -1 times R1. So 1 plus -1 0, and we get this. In the same way, now I can add R3 with -4 times R2, or multiply by -4 here and add with this. So it's gonna be 1 0 0 0 1 0 and 0. So we are multiplying by -4, 4 plus -4 is 0, and everything is 0. So this is what we get. In fact, this is in reduced row echelon form. So here is a pivot 1, here is another pivot, and this is x1, x2, x3, and this is free variable because we don't have a pivot column. So this implies, in fact, it's pretty simple here. x3 is free. Look at from the second row. From the second row we get 1x2. x2 equals 0. Okay. From the first row we get 1x1 equals 0. Okay, we get these two things, and x3 is free. Thus, like last time, we have x is x1, x2, x3, which is in this case x1 is 0, x2 is also 0, look at here, and x3 is free, just x3 for now, where x3 is arbitrary real number, so we can just factor x3 out. We get 0 0 1 as the basis for the eigenspace or corresponding eigenvector. 0 0 1 is the corresponding eigenvector for the eigenvalue lambda equals -3. So last time I left here for 5, we got 2 eigenvalues, and I just found for -3 I got 1 0 0 1 as eigenvector. Okay, these are eigenpairs, so we can just say in this way. Then thus D, the diagonal matrix, is just the eigenvalues. So 5, we got 2, so we need to write 5 twice, because 5 got 2 eigenvectors and -3. Or you can write -3 first, doesn't matter, and all others 0, because it's a diagonal matrix. And when we have a diagonal matrix, we can multiply this easily. Later you can exponentiate when you are doing differential equations, so this is really easy to handle. And the P matrix will be, look at this 5. This 5, now we can write one of these two eigenvectors. So 5 means just write one of them. -4 1 0 is a column, and for 5 another 8 0 1 and 3 in the third column, so this one. Okay, this is it. So we are pretty much finding A equals P D P inverse, and P inverse is easy to find, but that's not required here. So the issue here was to find D and P, diagonal matrix, and the invertible matrix P. Thus D and P, such that A is this. Or pretty much you can just find D and P and leave.